Hi, I'm Chaewon Gang, and I'm glad to present our work in ICTC 2022 conference. Our work is about the model that can efficiently predict traffic in a network that has less resource data, such as 5G or 6G network. As 5G and 6G networks evolve, efficient network resource management has become increasingly important to provide reliable and robust security guidelines and sufficient communication capacity. For critical communication, such as sharing secured, time-sensitive, or high-volume data, using public 5G networks where network resources divided fairly for all users may have a risk of deteriorating communication quality. To solve this problem, a private 5G and 6G network has emerged, which is operated as a separate and independent network targeting a specific purpose such as smart farming and smart factory. Especially in private 5G and 6G networks, which are emerging to address critical wireless communication requirements in public safety, infrastructure, and industry, predicting network traffic and prevent potential problems in advance is important. In addition, many device applications for communication require accurate resource allocation and bandwidth settings for reliable services. So, traffic prediction within the network is essential to control the congestion that may occur. Recently, network traffic can be accurately predicted by applying deep learning models. However, deep learning model generally requires a lot of data, and it's difficult to obtain sufficient data for emerging networks for newly built for specific purposes, such as private networks for smart factories. Therefore, we propose TransTraffic, a deep learning model that effectively learns and predicts future traffic volumes, even when there's not enough data, with the advent of new services in private 5G and 6G networks. Now, let me introduce the proposed model. The goal of the proposed model is to effectively learn and predict future traffic volumes given low resource data. To this end, our model employs two main components: traffic knowledge extractor and traffic predictor. The traffic knowledge extractor takes time series data as input to generate traffic representation. The traffic knowledge extractor consists of multiple transformer encoders, which consists of self-attention and feedforward layers. Then, by learning the traffic representation, the traffic predictor predicts the traffic volume for the next time step. To predict future network traffic with a small amount of data, such as newly generated 5G private network, we adopt the transfer learning method to train the proposed model. First, we train the entire model with large-scale data, and then fine-tune with a small amount of target data. Note that in transfer learning, the weights of the traffic knowledge extractor are frozen while fine-tuning. Let me introduce the dataset to train the proposed model. We utilize an open-source traffic prediction dataset, which collected from February 20th to October 6th in 2019. The dataset consists of network packets that contain timestamp of the packet, protocol, the size of the payload, source and destination IP address, source and destination UDP and TCP port, and the types of the user activity. There are 4 types of user activity: interactive, bulk, video, and web. Interactive activity includes traffic from real-time interactive applications, such as chatting app or remote file editing in Google Docs. Bulk data transfer activity consists of traffic to applications that use significant portions of the network's bandwidth for large data file transfers, such as large file downloads from Dropbox. Video playback activity includes traffic from applications consuming videos. And web browsing consists of traffic for all activities within a web page, such as downloading images or advertisements. Among the types of user activity, interactive data is used as large-scale data in transfer learning. More specifically, in the settings of our experiments, we first train the model with the interactive data. Then, we fine-tune the model with the rest of the user activities, which has a relatively small traffic volume. We split the dataset into the train, validation, and test sets with a 7:1:2 ratio. We also set the number of units, dropout rate, batch size, epochs, and learning rates to 100, 0.5, 128, and 0.0003 respectively. For model evaluation, we use R-squared, Pearson correlation coefficient, root mean squared error, and mean absolute error. Table 1 reports the traffic prediction performance of the multi-layer perceptron, LSTM, and the proposed model. As shown in Table 1, the proposed model outperforms both MLP and LSTM models in 3 different user activity data, especially with the extremely small amount of data, such as video and web. This indicates that the proposed model effectively extracts useful representation for future traffic prediction. Among the baselines, LSTM shows slightly better performance than the MLP. This may be because LSTM is designed to consider sequential information of the input features, whereas the MLP simply utilizes linear layers to model such information. To explore the effectiveness of the transfer learning, we compare the traffic prediction performance of the proposed model between with and without transfer learning. As shown in Table 2, the model with transfer learning method achieves better performance than in the opposite case. This reveals that applying transfer learning method is helpful in predicting lower source traffic data. So we proposed a deep learning model, TransTraffic, for predicting future traffic with lower source data. And the proposed model introduces transfer learning to accurately predict network traffic with lower source data. Our model shows higher performance than the baselines by learning common knowledge from a network with sufficient data and utilizing it together. We believe that our work can help manage network resource in 5G and 6G private networks, especially for a newly emerging service, hence no sufficient data can be obtained. So this is the end of my presentation. Thank you for your attention.